And we're on the air as we speak. All right, quietly now. Shh. Okay, so we are recording now. So, let's talk. Alrighty, so we're talking about sequences today. We're in 12.1, new chapter. Last chapter, by the way, in pre-calculus. We're going to switch to calculus after this chapter. All right, we're a little bit behind the times, a little behind we're behind the 8 ball. In that we should be done already with this book. We're supposed to do all the pre-calc stuff in one semester and then go to calc in the second semester. So we're going to take a couple weeks on here. We're a little bit behind, yeah. And that's to be seen. Maybe. Maybe, we'll see. I don't know. So we're going to take a couple weeks on this. And is it a couple weeks? Wait, go to it, Modo. And look, here's the assignment sheet, right? There it is. So, hang on. So let's see. Today we're doing, yeah, I know you full screen. This is what we're doing today. Tomorrow we're going over the homework. Then what's an arithmetic sequence? You did this in Algebra 2 and Trig, right? No? Okay, we're going to do some of the same stuff. All right, so arithmetic sequences, geometric sequences this week. No quizzy. No quizzy this week. She's busy with a test. Sorry. All right, and then we'll talk about geometric sequences and do a little bit more of that next week. Listen, shh. Then next week we're doing proof by induction. Oh, that's probably new. Did you do inductive proofs last year? No? Okay. All right, so there's a quizzy next Friday, not this Friday, next Friday, right before our enormous February break.
Our 1 day.
Yeah. So look, there's your break right there. See it, Monday? Yeah. No, not geometric. You'll see. You'll see what it is. And then we'll do the binomial expansion theorem, which you know so well already, don't you?
Yeah.
All right, and there's a testing there. So it's actually 3 weeks, including this week, okay, on this unit. All right, so. All righty, so let's start. It begins. It starts. All right, let's say I define the following sequence. You ready? Let's say I define, I don't know, let's be blue. Let's define the sequence A sub n to be n minus 1 over n. This is the rule. Now, these are n's. They're n's until they're not. I don't want to hear about it. All right, shush. Okay, they're all, when in doubt, it's an n. Ugh, everybody's a critic. Wait, all right. A sub n. Is that okay? No, that's an n. This is an n.
Stop putting the extra tail.
What, you want this? That's what you want? Nah, that's boring. Call it m if you want. I don't care. All right. So notice what's different here. We don't have a function of a continuous variable. We have a function of a discrete variable. What's the difference?
Is there a reason why you're putting it in those little bar things?
Because it's basically a set of numbers. Yeah.
I was going to say this.
Go ahead.
It's like discrete means it's singular, but it's like that is demonstrate and continuous.
Right. So you're not plugging in every single number for any. You're not plugging in like 2.5. You're not plugging in negative 12. You're plugging in whole numbers or integers. Like, can we start at 0?
Yeah.
Look at this one. Can you start at 0? No. So what's the smallest integer you can plug in? 1. Okay. Well, the smallest whole number, I should say. All right. So if we plug in 1, what do you get? A sub 1 is 0. A sub 2 is, plug in 2, what do you get?
2.
Really? 2? Really?
1 and a half.
1 half. Okay.
This later asked if you could come up with a period.
Okay. Deja, you've got mail. I know, I told her that. She said it at the end of the period. Alrighty. So, we plugged in 1, we got A sub 1. We plugged in 2, we got A sub 2. Plug in 3, you get A sub 3. What's A sub 3 going to be? Huh? 2/3? Okay. 2/3. A sub 4?
3/4.
3/4. Okay. And how about A sub 5?
5/9.
No. 4 4/5, right, and so forth. All right, let's say this is a finite sequence. What does that mean? It stops, right? Is there such a thing as an infinite sequence? Yep, we'll talk about that. Okay. What's a series?
It's a set of.
The sequence is a set. It's a set of ordered values, right? But what's a series based on that sequence? Do you know what a series is?
Are they subsets?
No? No? Huh? Nope. No. You don't remember what a series is? Where were you last year? Didn't you do this stuff last year?
No.
This should be easy review stuff. No? A series is nothing more than the sum of the sequence.
Oh, it's a difference.
Yeah, add them up, okay? All right, but right now we're just talking about sequences, that's all. All righty, how about this one? What if I gave you the sequence... Hello, wake up. What if I gave you the sequence B sub n? Yeah?
How do you have a series of an infinite sequence?
That's what we're going to find out. Sometimes it doesn't exist. If you add up infinitely many terms, you would expect it to blow up and be infinite, not a number, right? But sometimes you do get a number. We'll talk about that. All righty. That's a B sub n. Okay, B1 with your inner sequence. Okay, so let's say, now look, this one's different. What if I say -1 to the n minus 1? What are you talking about? Okay, to the n minus 1. That's an n.
It's this about it. No, negative word.
All right, whatever. Of times 2 over n. Okay? All right, so can you plug in 0?
No.
No, so plug in 1. What happens? Well, 1 minus 1 is, and anything to the 0 is 1, and 2 over 1 is 2. So a sub 1 is 2. What's a sub 2? 2 minus 1 is 1. Negative 1 to the 1? Negative 1. And 2 over 1? Negative, 2 over 2, I should say. We plugged in 2, right? So negative 1. Is this terrible?
Yes.
Not really. All right. What if you plug in 3? What's b sub 3? 3 minus 1? 2. Negative 1 squared? Positive 1. And 2 over 3? So positive 2/3? Okay. All right. That's b sub 1, b sub 2, b sub 3. How about b sub 4? B sub 4 would be negative, okay? Because 4 minus 1 is 3, and negative 1 to the 3rd is negative 1.
So these are all true when you're solving for integers, right?
This is only integers, right?
So what if you'll never be, what if you get asked these decimals?
Well, the numbers in the sequence may be fractions or decimals, but you're plugging in whole numbers for n.
They don't specify?
If they don't specify, plug in the smallest whole number you can. Like I said, can you plug in 0? No. So start at 1. For what? What was the question? Oh, the next one? All right, if I plug in 1, 2, 3, 4, if I plug in 5, is it negative or positive? Positive, and 2 over 5 is 2/5 or 0.4. Yeah. All right, but I'm stopping there. Let's see. How about this? All right, let's go backwards. What if I gave you a sequence? Could you give me the rule?
Yes.
Right? I gave you the rule, and you gave me the sequence, right? Now let's go backwards. What if I gave you this? Your sequence looks like this. E squared over 2, e cubed over 3. What's the pattern? Do you see a pattern? E to the 4th over 4. No, stop with the logs. Equals what rule in general? E to the n over n, that's all. And n has to start at 1, yeah. No, I'm not dividing the 4 by 4. I'm dividing the whole thing. E to the 4th over 4. Right, the whole thing. I'm dividing e to the 4th over divided by 4. E to the 3rd divided by 3, right? Yeah, I know. It's sloppy. Yeah. That's the series. We're going to do that. That's what a series is, the sum. Now, this section isn't about series yet. We'll get to that. Okay. All righty. How about this one, then? Let me think. Okay. Well, let me ask you this. Do you know if that's arithmetic, geometric, or neither? Do you know?
It's arithmetic.
Is it? Yeah. What makes it arithmetic? If you add the same amount every time to get the next term, right? Well, whatever, I don't know what the heck you're adding to get this, but is it the same thing you're adding? I don't think so. Is it geometric? That means you're multiplying by the same common ratio? Let's see, I multiply by e over 2. I multiply by e over 2. No. It's not geometric.
It's neither.
It's neither. All right, how about this one? Here's a pattern. I'm going to ask you first, give me the pattern. Here's the sequence, give me the rule. And second, is it geometric, arithmetic, or neither? All right, so here we go. 1, 1/3, 1/9, 1/27, and so forth, forever. This is an infinite sequence, goes on forever. Can you give me the rule? What do you think?
Times 1/3.
Multiply. Okay, so it's that geometric, arithmetic, or neither?
N times 1/3.
N times 1/3. No.
Over 3n.
1/3n. 1/3 to the n. Powers of 3. And starting with n equals? 1? No. Not this time. N equals 0 this time, right? Because 3 to the 0 is 1, and 1/1 is 1. That's what we're starting with, right? Well, because what do you get? How do you get from here to here? Multiply by a third. How do you get from here to here? Multiply by a third. How do you get from here to here? Multiply by a third. So it's powers of 1/3, really. But powers of 1 is always 1. So is this geometric, arithmetic, or neither, by the way? Geometric. If you multiply by the same common ratio every time. Huh?
What is this? What is
The common ratio here is 1/3. 1/3, yeah. If you can multiply by the same amount each time to get the next term, the next term, the next term. Multiply by a third, you get this. Multiply by a third, you get this. Multiply by a third, you get this. Geometric. In this case, what you're multiplying by is called the common ratio, because it's the next one divided by the previous one is 1/3. And if that ratio is in fact common, it's the same everywhere, it's geometric. If you add the same amount every time, it's arithmetic. That's called the common difference, right? Like, I don't know, let me make up something. 2, 4, 8, 2, 4, I did it wrong. All right, wait, let me do that. What is 2, 4, 8, 16, 32? Is that geometric, arithmetic, or neither? Geometric, because it's powers of 2. But I meant to write 2, 4, 6, 8, 10. Now that's what? Arithmetic, because you're adding 2 every time. That's a common difference. All right, it's called the common difference because any term minus the previous term is 2. Any term minus the previous term is 2. This is called the common ratio because any term divided by the previous term is 2. Any term divided by the previous term is 2. Common ratio, common difference, geometric, arithmetic, geometric, right? All right, so what's the general rule then? What would this be? 2 to the n. Okay. What about this one? Do you know how to write an arithmetic?
N plus 2.
Huh? N plus 2
No.
always? No, not always.
To the blank. To the n.
I'll give you a hint. It's sort of like mx plus b.
What?
It's sort of like mx plus b. What if you plot this? What if you plot the point
Is it 2 times n?
2 times n, right? Isn't it?
Yes.
It's like, what if you plot the point 1, 2, 2, 4, 3, 6, 4, 8. Aren't you getting a line with a slope of 2 and intercept of 0 in this case? If you plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6, right? So arithmetic sequences can be written sort of like mx plus b stuff, and geometric sequences are usually powers, right? Exponentials, I should say. Well, if the end is on the whole thing, you could write it this way. I could have written it this way instead. The common ratio, all to the n. To the 0 gives you 1. To the 1 gives you a third. To the 2 gives you 1/9. Because 1 squared is still 1. To the third is 1/27th. Because 1 cubed is still 1, but 3 to the third is 27. You could write it that way. Well, practice, practice, practice. Don't forget your homework tonight. It was here. Where is it? That's Tuesday. There it is. Homework tonight, page 821, multiples of 10. We'll go over that tomorrow. Any homework checks tomorrow? All right. Let's see. How about this one? What if I gave you, all right, think. What if I gave you this? 1, 2, 6, 24, 120. Does anyone know this sequence?
No.
No?
Geometric, isn't it?
Is it geometric? Times 2. Times 2? No.
No. No, it's 10.
Anyone know what this is?
Like,
It's n something. It's a function in n. Yes, it is. It's a discrete function that you know. I'm sure you know this discrete function. What? Not a power. This one's weird.
is it a log?
Okay, tell me. Right. You know what that is? This is, the first term is 1. The next term is 2 times 1. The next term is 3 times 2 times 1. The next term is 4 times 3 times 2 times 1. This is factorial. Yeah.
Factorial.
Yay, factorial. Right? All right, all right, all right. All right, what about this? This is a recursive formula. Let me show you. All right, let me think. Hang on. Here's an example of a recursive formula. Let's say I tell you that a sub 1 is 1 and a sub 2 is 1. But from then on in, a sub n plus 1 is a sub n plus a sub n minus 1. In other words, the next value is based on a previous, in this case, previous 2 values. We call that recursion. So can you tell me what a sub 3 is? It's a sub n. A sub n plus 1 is 3. So what's n? 2. All right, so a sub 2 is 1. And a sub, who is this? A sub 1, right, is? So 1 plus 1 is 2. So what's a sub 4 then?
It's 3.
How do you know? A sub 4 is, n is 3, right? If n plus 1 is 4, n is 3. So I need a sub 3 and a sub 2. Well, what's that? I didn't do that. So it's a sub 3 plus a sub 2 is 3. All right, let's go over here. What's a sub 5?
5.
It's going to be a sub 4 plus a sub 5, which is 5. Have you ever seen this sequence? What's a sub 6?
8.
8. What's a sub 7?
13.
13. That's an equal sign. What's a sub 8?
1.
What? Who? 1 1?
21.
21. Okay. Anyone know this sequence that has a famous name? Well, it's famous. It was named after what? Fibonacci. The Fibonacci sequence is recursive. It's the next term is based on a previous term or more than one term. All right. How about, what if I gave you some sigma notation? You familiar with that? What does it mean? Sigma, right? Sigma is just capital what in Greek? No. Sigma is capital S in Greek. It's chosen on purpose because we're finding a sum. Right, exactly. So what if I say k goes from 1 to, I don't know, 1 to 3, and the rule is 1 over k. What am I doing? Plug in 1, you get 1. Plug in 2, you get 1/2. Plug in 3, you get 1/3, and then add them up. That's a 3. Ugh. It's so hard to do this on a tablet.
No, it's a K.
Okay, and so we're adding. Well, it's a K unless it's not. When in doubt, it's a K. All right, so how do you add fractions, by the way? Common denominator here is, so multiply top and bottom by 6, and you get 6, 6, plus 3, 6, plus 2, 6 is 11, 6. Right. Okay. All righty, good. How about this one? What if I said, what's the sigma of k factorial if k starts at 0 and goes to 3? Well, that's going to be what? 0 factorial plus 1 factorial plus 2 factorial plus 3 factorial. But we just figured out 3 factorial was, did we just do this a minute ago? 3 times, 2 times 1. 6. 2 factorial is 2. 1 factorial is 1. And 0 factorial is 1. 7? That's a new one. Most people say 0. Why is 0 factorial 1?
I forget. Anything to the 0 power?
It's not a power, though. So yeah, that makes sense, sure. All right, so what's the sum, by the way? 10, right? Okay. All right, this is not tough. Why is it 1? Because God said so. It's not a multiple. It's not a product, though. Because God said so. In this case, God is my dog. My dog is named after famous French mathematician that said 0 factorial must be 1. You ever hear of Pascal? Pascal's triangle wouldn't work unless 0 factorial were 1. No, and dog backwards is God. You got it. Finally, somebody got that joke. Nobody gets that joke. All right. You don't understand. I adopted this dog from one of those, rescue a pet thingy.
Oh, like the commercials?
Yeah. And they, for some reason, it was a little nothing at the time. They thought it was going to be a Dalmatian, so they thought it was, hey, it's a firehouse dog. Good for a fireman, right? Let's call him Blaze. First, it wasn't him. Second of all, I am not calling her Blaze. I'm calling her Blaze.
Blaze Pascal.
Blaze Pascal.
Oh.
Blaze Pascal is spelt not B-L-A-Z-E as they thought. B-L-A-I-S-E, right. So, yeah, my dog is named after Blaze Pascal. Well, because the dumb dog wouldn't change her name. They called her Blaze at the rescue center, and I tried to change the name to something else, and she would never come. So I said, all right, fine, your name is Blaze, but I'm spelling it different. It's whatever. So, all right. Can you? All right. Let's see. What else is good here? All right, take a look at the homework page. Page 821. Okay, let's take a look at some examples from 821. Okay? Now, you have the multiples of 10 tonight. Let's do something like that. Let's say...
Let's do number 10.
Well, no, you're doing number 10. All right, write the first 5 terms of this sequence. How about number 7? Here we go. All right, number 7. This is page 821. Number 7 says the sequence is 2 to the n over 3 to the n plus 1. Actually, I messed it up, but anyway. Because I feel like it. Look, it's a free country until Obama gets elected, all right? So, what? What happened? Okay. So, what's the smallest value of n you can plug in? Can you plug in smaller? Sure you can. What's the smallest whole number there is? 0. Can you plug in 0? What's 2 to the 0? 1 over, what's 3 to the 0? 1 plus 1 is 2. Good. All right, they want 5 terms, so that's what they're getting. Plug in 1. 2 to the 1 is?
So this is what we're doing?
2. This is homework tonight, yeah. Now, what's 3 to the 1 plus 1? 3 to the 1 plus 1? 4. All right, we plugged in 0, we plugged in 1. This is, plug in 2. So 2 to the 4th, 2 to the 2nd, is 4. And 3 to the 2nd, 9 plus 1 is 10, which does reduce, I guess. All right, you don't have to. And now we plugged in 0, plugged in 1, plugged in 2, plugged in 3.
The top one is
8 over 28. Okay. And plug in 4. 16 over 80. 80?
81.
2, actually, because it's 81 plus 1. Don't forget the 1. All right, that was an example from the homework. This is not tough. All righty.
Okay, now do number 10.
All right. Okay, take a look at 29. You're doing 10, 20, 30, 40, right? Look at 29. 29 says, a sub 1 is given, it's 1. A sub 2 is given, it's 2. And a sub n, the next one, is a sub n minus 1, the previous one, times n, a sub n minus 2? The one before that. So, what is a sub 3? 2. What's a sub 4? 4. What's a sub 6? Sorry, a sub 5? 8, and so forth. They wanted 5 terms, there they are. Yeah.
But when you do this recursive form, why are you to assume that A of n is 1 larger than whatever the previous one is?
Well, because I know those two, so I'm going to use them to get the next one. I know a sub 1, a sub 2, let's get a sub 3.
But that's assuming that they have the same discrete part.
No, that's assuming that a sub 3, where's my tablet? A sub 3 is a sub 2 times a sub 1. That's what this is saying. A sub 3 is a sub 2 times a sub 1. A sub 4 is a sub 3 times a sub 2. A sub 5 is a sub 4 times a sub 3. I guess so, yeah.
Did they give you that formula?
Yeah, that's given. This is given. Let's see, what's given? You know, why do we kill trees? Turn to page 821. This is given, this is given, this is given. Yeah, sort of. Okay. Alrighty. So that's all this is. Some sequence notation, some sigma notation, not a big deal. How about this one? 49. 49 says, well, I can't write today. 49 says, there you go. What's sigma? As k goes from 1 to n, I don't know what n is, but it's bigger than 1, of k squared over 2. What does that mean? Well, n can be any integer greater than 1. So what we're going to do is going to show a pattern for, say, I don't know, 3 terms, and then stop at n, whatever it is. So what if you plug? What do you start with? You plug in? 1 squared is? 1 over 2 is? Well, 1/2. All right, now remember, sigma is, don't just list it, add it, right? All right, so k is what now? 2. So 2 squared is 4 over 2 is 2. Plus, k is what now? 3. 3 squared is? 9 over 2 is? Well, you can write 9/2 if you want. 4.5, whatever. Plus, you know, if you're actually going to add this up in your head, it'll be easier to put decimals. But what if we just stop now? What if you plug in n? What do you get?
You get 60.
Dot, dot, dot. No, plug in n. Wherever you stop, it doesn't have to be 4. N squared over 2. Okay? All right, now, how do you do this on the calculator? Can you? Let's see. Can we do this on the calculator? Have you ever done sequence mode on the calculator? Ooh. Oh, this is fun. Are you ready? All right, first make sure your mode is, guess what? I'm going to graph this stuff. Mode is sequence mode. Ding, ding, ding. Ding, ding, ding. Enter. All right. Then when you hit y equals, guess what? You don't get y equals. All right. Shh, focus. All right, so u sub n is the rule. So let's put that in. Now it's in terms of n. They have in terms of k. I'm doing it in terms of n on the calculator. Now n is an actual character on here. Where the heck is it?
It's the X button.
The X button?
The X is supposed to be.
There it is, yeah. All right, so let's write in n squared over 2. Ready? So n, notice you're not getting x. Now it's not really an n. It's a nu. It's a lowercase n in Greek. Nu. Okay, I'm going to square it and divide it by 2. Isn't that the rule? Okay, so what I'm going to do, first of all, is I'm going to generate the sequence, because this is sequence mode, remember. Mode, sequence mode. It doesn't know series mode, it knows sequence mode. So it's just going to generate the numbers. All right, go into your window. What was this first value of k that I plugged in?
1/2.
No.
Oh, sorry, 1.
1. So shall I start with 1? Shall I start with 1? Yeah, that's what that means. They're using n, they used k, big deal. All right, let's say I type out the first 10 elements of this thing. The 1/2, the 2, the 4/2, and 7 more. Let's let the calculator do stuff like that. Don't worry about this, don't worry about this. This x-min, I usually start at 0. X-max, I usually stop at n-max, which is 10. And x-scale is 1 is fine. So, graph. Now what happened? Well, let's see. Trace, you get 0.5. Why is that good? Why is 0.5 good? Because that's the 1/2. All right, trace to the right 1. I get 2. Why is that good? Because it's 2. Duh.
Wait, so is this discrete?
This is discrete. It's right. Look at what a discrete graph looks like. It's not connected. They're separate dots. The problem is it goes way off the screen. How big do you think it gets if I plug in up to 100? Well, 100 squared is? Sorry, plug in up to 10 they wanted. So, right, remember my window. I'm going up to n max is 10. So if I plug in 10, what's the most I get? 10 squared? 100 divided by 2? 50. So change your window to include a y max that big. It's not big enough, my y max. So my y min can be 0 because I don't have any negatives. My y max has to be at least 50. Let's make it 100. So how about a scale of 10? Now let's regraph it and see what we get. And these are the terms. Trace. 0.5, is it? What do I multiply 1/2 by to get 2? By 4, actually. 4 times 1/2 is 2. If I multiply that by 4, do I get this? It's not geometric then. It's neither. Yeah, it's not. But look what you get. You got 0.5, you get 2. You got 4.5. What would be the next term? We plugged in 1, 2, 3. What if we plugged in 4? What if we plug in 4? 16 over 2 is 8, right? Let's see what we get. Next term on here is, ta-da, 8. All right, what if you plugged in 5? 25 squared over 2 is 12.5. Ta-da, it's here. All right, now how do we fool the calculator into adding? The calculator doesn't have sequence mode. Look at the mode. Sorry, it doesn't have series mode. It has sequence mode. It can only graph these values. I'm gonna cheat. Are you ready? I'm going to make it recursive. I'm going to make it add the new value onto the previous value that it graphed. All right. So go to y equals and do second delete is insert alpha u. Where's my u? No, that's not it. Dang it. I want alpha u. There you go. No, that's not it. Wait, that's not it. Hang on. I need, yeah. All right, clear that. Where's the U on here? Yeah, is it alpha U? Wait, I'm not sure if it's alpha U. Wait. Is it, there's a symbol for this. It's lowercase u. Where the heck is it? Yeah, I don't think that's it though. It's on 7? Yeah, I think it's 7. All right, second 7. I think that's what it is. Second 7, that's it, of n minus 1 plus what you had, n squared over 2. So this is a recursive rule. It's going to plot the first one, then the first 2 added up. So it's going to take the previous one plus the new one. Then it's going to take the new one plus the previous 2. Then it's going to take the new one plus the previous 3. And it's going to graph a sequence of partial sums. This, then this was this, then this was this. Eventually the last value is the total sum of everything. All right, so the problem is, though, I have to tell it where it starts. What's the first value? 1/2. It doesn't know how to start. All right, so tell it the first n value and the first u value and graph that. Now that goes way off the screen. But if you trace it, look what you get. 0.5, then 0.5 plus 2, then 0.5 plus 9/2. Then 0.5 plus, what was it? 4. I'm sorry, wait. It's 0.5 plus 2. It's 2.5 plus 9/2. It's 7 plus 8. It's 15 plus whatever it was. 1, 2, 3, 4, 25 halves, which is 12.5, and so forth. So if I'm summing the first 5 terms, if I stop at 5, the sum is 27.5. So we can fool the calculator, even though we're in sequence mode, to do series of partial sums, graphing each individual sum. The last one is the sum of the whole thing. Okay, so we're practicing this up tomorrow. So your homework tonight, multiples of 10, page 821, 822, 823. Oh boy, what fun you're having. 10, 20, 30, 40. And that's all she wrote, baby. All right, so I'm gonna tell YouTube goodbye. Bye, YouTube.
Bye, YouTube.